These can be some of the most difficult integrals to recognize. For some reason, sometimes they're hidden. So sometimes hidden forms of the logarithm rule will show up in situations like this. So anytime you've got a rational expression that you're trying to integrate and the degree of the numerator is greater than or equal to the degree of the denominator, like in this case they have the same degree, you want to try long division because it may allow you to actually integrate, whereas you couldn't before. So I'm going to start off with x squared plus x plus 1, and I'm going to divide by x squared plus 0x plus 1 because that's my missing term here. So this will give me 1 out of x squared plus 0x plus 1. I change the signs, and the only thing I have left is x. So the answer here is 1 plus x over x squared plus 1. So this is the integral of 1 plus x over x squared plus 1 with respect to x. Or if I split it up into 2, I'd have the integral of 1 dx plus the integral of x divided by x squared plus 1. With respect to x, the integral of 1 is just x. In this case, if I let u be equal to x squared plus 1, u prime would be 2x, so I need a 2 here, which means I need to multiply by 1/2 on the outside to cancel it. So this becomes 1/2 times the integral of u prime over u dx, or x plus 1/2 times the natural log of the absolute value of u plus c, and that u is x squared plus 1 plus c. If you want to fold that in and make that x plus the natural log of the square root of x squared plus 1 plus c, you can. You don't have to. Either one of these would be a perfectly valid answer. Now on this one, because I am dividing x squared plus x plus 1 divided by x minus 1, I could use long division, but I could also use synthetic division. So if you remember how to do that, it only works when you have x minus some c. So since I'm dividing by x minus 1, that means c is equal to 1. So if I'm looking at x squared plus x plus 1, I would have a 1 coefficient, 1, 1. And I'm going to bring down my 1, so 1 times 1 is 1, which gives me 2 when I add. 1 times 2 is 2, 1 plus 2 is 3. And the way you interpret this is you start with 1 power or less, so this would be x plus 2, and then this is my remainder, 3 over x minus 1. So I'm integrating x plus 2 plus 3 over x minus 1. Remember, if you do long division, you get the same answer. This is just a special type of division that works for this particular case. So this is the integral of x with respect to x plus the integral of 2 with respect to x, plus I'm going to go ahead and bring the 3 out and make that 1 over x minus 1 with respect to x. This one is x squared over 2. This one is 2x. And then over here, if I let u be equal to x minus 1, u prime would be 1. So this is the integral of u prime over u dx. So I'm going to have 3 times the natural log of the absolute value of u, all plus c. So I get x squared over 2 plus 2x plus 3 times the natural log of the absolute value of x minus 1, all plus c. And I'm just going to leave my answer there. There are some cases where trig functions are actually hidden natural logs as well. So if you were to write tangent of x as sine of x over cosine of x, because that's an equivalent way to say it, if we let u be equal to cosine of x, u prime would be negative sine of x. So if I multiply by a negative out here, I would have a negative out here also in order for those to cancel out. And this becomes negative integral of u prime over u dx. So I could write that as the negative natural log of the absolute value of u plus c, or the negative natural log of the absolute value of cosine of x plus c. And that would be my answer there. So I'm going to let you try the next one. It's very, very similar, and see what you can come up with. Now this one is definitely not obvious. If you were to try and make this 1 over cosine of x dx, you know, if your u is cosine of x, your u prime would have to be negative sine of x. So we don't have a u prime here, so this doesn't help us. We don't want to do this. There's actually a trick to this one, and I wouldn't expect you to know this off the top of your head. This is something I'm going to show you. So the trick to the integral of secant of x is to multiply by this fraction. Now, as long as I don't move any of these things that I'm going to multiply out of the integral, it's okay, because I'm going to multiply by secant x plus tangent x divided by secant x plus tangent x. Now that's just 1 because they're the same on top and bottom. And again, as long as I don't move anything out of the integral, there's nothing wrong with doing that. So now I'm going to distribute the secant x on top, so that's the integral of secant squared of x plus secant x tangent x divided by secant x plus tangent x. And I'm actually going to take this one step further. I'm going to swap the order of the top, so that'll be secant x tangent x plus secant squared of x. I think you'll see why I did that in just a second. Divided by secant x plus tangent x. Now if I were to let u be secant x plus tangent x, then u prime would be the derivative of secant x, which is secant x tangent x, plus the derivative of tangent x, which is secant squared of x. So this is the integral of u prime over u dx. It's just kind of messy. But that's simply the natural log of the absolute value of u plus c, which is the natural log of the absolute value of secant of x plus tangent of x, all plus c. So that is my answer. And you could do something very similar for the integral of cosecant of x. I'll leave that one for you to try and verify yourself. So this leads us to define several more trig function integrals. We already knew the integral of sine of u and cosine of u, but now we can talk about the integral of tangent of u. It's equal to the negative natural log of the cosine of u plus c. The integral of cotangent of u is the natural log of the absolute value of sine of u plus c. Secant of u, it's the one we just found, and I would encourage you to try and find this one. It'll be very similar. There is a trick, but you should be able to figure out what that is. Now this is just kind of a neat little problem that uses one of the formulas we just saw. So I've got 1 plus tangent squared of x dx. Now you cannot just take the square root and make that 1 plus tangent of x. That does not work. What you have to do is use a Pythagorean identity in order to convert this to something where the square root is going to cancel out. So the most basic Pythagorean identity is that sine squared of x plus cosine squared of x is equal to 1. This is something that I expect you to know. I'm not going to give you this, but you can derive the other two versions of the Pythagorean identity from it. So if I were to take this, sine squared of x plus cosine squared of x equals 1, and divide through by sine squared of x, just both sides of the equation, I get that 1 plus cotangent squared of x equals cosecant squared of x, so that's one form of it. And if I were to take the original Pythagorean identity and divide through by cosine squared of x, I get that tangent squared of x plus 1 equals secant squared of x. So this is the version that's going to be interesting to me right now because I have the square root of 1 plus tangent squared of x dx. So according to the Pythagorean identity, that is the square root of secant squared of x dx. And because you can verify that secant of x is positive from 0 to pi over 4, the square root of the secant squared is going to be the integral of the secant of x. And we know that this is equal to the natural log of the absolute value of secant x plus tangent x. We just verified that. And that's going to be from 0 to pi over 4. So if I'm evaluating this as a definite integral, that'll be the natural log of the absolute value of secant of pi over 4 plus tangent of pi over 4 minus the natural log of the absolute value of secant of 0 plus tangent of 0. And if I have a right triangle, now pi over 4 is an isosceles right triangle. Going back to my my trig with my standard 45, 45, 90 triangle, the cosine of pi over 4 is 1 over the square root of 2, and that means that the secant of pi over 4 is going to be 1 over that, so that'll be the square root of 2. And the tangent of pi over 4 is going to be 1 over 1. So this is the natural log of the absolute value of the square root of 2 plus 1 minus the natural log. Cosine of 1, cosine of 0 is 1, so secant of 0 is also 1, and tangent of 0 is 0. So I get the natural log of the absolute value of square root of 2 plus 1 minus the natural log of the absolute value of 1. The natural log of 1 is 0. And because the square root of 2 plus 1 is positive, we don't need the absolute value bars anymore. If you left them, that would be fine, but you don't need them. But what you can do here is go ahead and put the parentheses on here. So this one's going to go away. It'll be 0. I like to put the number in front of the square root just because it's a little bit clearer. Either way is fine. But this would be your final answer.